In 2024, something extraordinary happened. A company that doesn't make smartphones, doesn't run a social network, and doesn't control an operating system briefly became the most valuable corporation on Earth. A company built on silicon and parallel math overtook every giant of the last generation. Apple, Microsoft, Google. Its headquarters? A glowing tower of glass and circuitry. Its product? Chips that power the future. But NVIDIA's story didn't begin with AI, or trillion-dollar valuations, or data centers stretching across the world. To understand how a graphics company became the engine of the modern era, we have to leave the neon skyline of today and travel back to a time when computers were clumsy, slow, and practically blind. A time before GPUs, before machine learning, before realistic graphics. A time when three engineers sat in a diner in San Jose, sketching ideas on napkins that would quietly redefine everything. Picture this. It's 1993. The personal computer revolution is in full swing, but there's a problem. Computers can't really see. They can calculate, sure. They can process spreadsheets and Word documents. But ask them to render a three-dimensional world, to create the illusion of depth and light and shadow. They're practically blind. Three engineers meet at a Denny's in San Jose. Jensen Huang, Chris Malachowski, and Curtis Prim. They're scribbling on napkins, arguing about the future. And what they're designing isn't just another computer chip. They're designing a new way of thinking about computation itself. They name their company NVIDIA. The origin of the name? It comes from NVIDIA, the Latin word for envy. But Huang will later say it also evokes nvda, to see. Both meanings turned out to be prophetic. But here's what makes NVIDIA's origin story different from every other Silicon Valley garage tale. They were solving the wrong problem. Or rather, they were solving a problem that would turn out to be merely the first act in a much larger drama. In the mid-90s, the graphics card market was chaos. There were dozens of companies, all fighting to render polygons faster than their competitors. The goal was simple: make video games look better. That's it. That was the entire market. NVIDIA almost died in those early years. Their first two chips, the NV1 and NV2, were technical disasters. The NV1 used quadrilaterals instead of triangles for 3D rendering, a decision that sounds technical and boring until you realize it made the chip incompatible with the direction the entire industry was moving. It was like building a car that could only drive on hexagonal roads. By 1997, NVIDIA was on the brink of bankruptcy. They had one more shot. The NV3, branded as the Rivier 128, launched in 1998. It wasn't just good, it was revolutionary. It could process 3 million polygons per second. It supported DirectX 5, and critically, it was affordable. NVIDIA survived. But survival wasn't the interesting part. What happened next was, in 1999, NVIDIA coined a term that would define the next 2 decades: GPU, Graphics Processing Unit. This wasn't just marketing. It was a reconceptualization of what these chips actually were. A CPU, your computer's main processor, is like a brilliant mathematician working through problems one at a time, very quickly. A GPU is like having 10,000 mediocre mathematicians working on 10,000 problems simultaneously. For certain types of work, particularly anything involving massive parallel calculations, the 10,000 mediocre mathematicians win every single time. Jensen Huang understood something crucial. The architecture they'd built for graphics wasn't just good at graphics. It was good at any problem that could be broken into millions of parallel operations. The question was, what other problems fit that description? The answer came from an unexpected place: academia. In the early 2000s, researchers started noticing something strange. They could run scientific simulations on NVIDIA GPUs dozens of times faster than on traditional supercomputers costing millions of dollars. Problems that required massive parallel computation. But there was a problem. Programming GPUs required you to essentially trick them into thinking they were rendering graphics. You had to translate your scientific problem into pixels and vertices and shaders. It was absurd. Brilliant, but absurd. In 2006, NVIDIA made the most important decision in its history. They released CUDA, Compute Unified Device Architecture. It was a programming platform that let developers access the GPU's parallel processing power directly, without pretending they were making a video game. Wall Street hated this decision. NVIDIA was spending hundreds of millions of dollars on software development for a market that barely existed. The video game market was growing. Why dilute focus? Why invest in scientific computing when gamers were paying premium prices for graphics cards? Jensen Huang's answer was visionary. We're not building graphics cards. We're building parallel processing platforms that happen to be really good at graphics. For 5 years, this looked like an expensive mistake. The scientific computing market was niche. NVIDIA's stock languished. And then everything changed. The ImageNet competition. It's a contest to build artificial intelligence that can recognize objects in photographs. For years, progress has been incremental. Error rates are stuck around 26%. A team from the University of Toronto, led by Geoffrey Hinton, enters a system called AlexNet. It's a deep neural network, essentially a software structure loosely inspired by how brains process information. But unlike previous neural networks, AlexNet is trained on NVIDIA GPUs using CUDA. AlexNet achieves a 15.3% error rate. It doesn't just win, it doesn't just beat the competition. It obliterates every assumption about what's possible. The runner-up achieves 26%. AlexNet is in a different universe. And suddenly everyone realizes, the thing that makes GPUs good at graphics, parallel processing of massive amounts of data, is exactly what makes them good at machine learning. Training an AI is fundamentally about doing the same mathematical operation billions of times on different pieces of data simultaneously. NVIDIA had accidentally built the perfect tool for the AI revolution. Except it wasn't an accident. It was the result of a decade-long bet that parallel processing would matter for more than video games. Within 2 years, every major AI lab in the world is running on NVIDIA hardware. Google, Facebook, Microsoft, Amazon, they're all buying GPUs by the thousands, then by the tens of thousands. But here's what separates NVIDIA from every other hardware company. They don't just sell chips, they build an ecosystem. CUDA isn't just software, it's a moat. By 2015, there are thousands of researchers and engineers who've spent years learning CUDA, building libraries in CUDA, optimizing algorithms for NVIDIA's architecture. Switching to a competitor would mean rebuilding everything from scratch. It's the same playbook that made Windows dominant in the 1990s. Except instead of regular users, NVIDIA's locked in the world's most sophisticated AI researchers. 2016, NVIDIA releases the DGX-1, their first system designed specifically for AI. It costs $129,000. It sells out immediately. 2017, NVIDIA's stock price passes $100 for the first time. It had been under $10 just 5 years earlier. 2018, NVIDIA introduces tensor cores, specialized circuits built into their GPUs specifically for the matrix operations that neural networks use. They're not even pretending it's about graphics anymore. And then, November 2022, everything changes again. OpenAI releases ChatGPT. Within 2 months, ChatGPT has 100 million users. It's the fastest growing consumer application in history. And every single word it generates, every response it creates, runs on NVIDIA GPUs. Suddenly, AI isn't a research curiosity. It's the most important technology on the planet. Every company needs an AI strategy. Every AI strategy requires massive amounts of computation. And 90% of AI computation runs on NVIDIA hardware. The demand is insane. NVIDIA's H100 chip, their top-of-the-line AI accelerator, officially costs $30,000. On the gray market, they're selling for $40,000 to $50,000. And there's still a waiting list measured in months. Tech companies are ordering GPUs like they're hoarding resources for the apocalypse. Meta announces they're buying 350,000 H100s. Microsoft, Google, Amazon. They're all in an arms race, spending tens of billions of dollars on NVIDIA hardware. In May 2024, NVIDIA's market capitalization crosses $2 trillion. In June, it briefly becomes the most valuable company in the world, surpassing both Microsoft and Apple. A company that makes computer chips is worth more than the iPhone maker. Let that sink in. But here's where the story gets complicated. Because NVIDIA's dominance raises questions that Silicon Valley doesn't like to talk about. First, the concentration of power. AI development now has a bottleneck. If you want to train a frontier AI model, you need thousands of NVIDIA GPUs. If NVIDIA can't supply them, or if geopolitical tensions disrupt the supply chain, AI development grinds to a halt. We've built the most important technology of the 21st century on a single point of failure. The US government understands this. That's why they've placed strict export controls on NVIDIA's advanced chips to China. It's not just trade policy. It's an attempt to maintain technological hegemony. NVIDIA has essentially become a weapon of geopolitical competition. Second, the competition problem. NVIDIA's competitors, AMD and Intel, are desperately trying to catch up. But they're not just fighting NVIDIA's hardware. They're fighting a decade of software optimization, thousands of trained engineers, and the network effects of an established ecosystem. Google has developed their own AI chips, the TPUs. Amazon has Inferentia and Trainium. Microsoft is investing in custom silicon. These tech giants understand the danger of depending on a single supplier. But even with unlimited resources, catching up takes years. NVIDIA's current architecture is extraordinary, but it was designed for graphics in 1999 and adapted for AI in 2012.